Okay, in this part of the presentation, I want to explain how we can compute our alphas, which are mainly the confidence that we have on each of our weak classifiers. So in the previous algorithm, you saw that in step 2, you need to update alpha using this formula here. So we are going to derive this formula in this part of the presentation. And also, you will see that the error of our strong classifier, when you train it using AdaBoost, is upper bounded by the number of weak classifiers that we decide to train. So first, let's see that the error should be less than 1 for any given weak classifier. Okay, and if that is true, then our alpha, which is computed using this expression here, will be a positive number. So this is something true that you can verify with every value of epsilon that is less than 1. Of course, we have said before that the minimum or the maximum error that we can accept for a given weak classifier is a number less than 0.5. But this is just an analysis of what values can take epsilon, and if this is less than 1, then it is true that alpha should be a positive number. So just keep in mind that alpha is a positive number. And also, as I have mentioned before, if given two weak classifiers A and B, if the error of A is less or smaller than the error of B, that means that the alpha of A is going to be larger than the alpha of B. So given two weak classifiers, we are going to trust more on that classifier with the smallest error, which in this case is the weak classifier A. Okay, now look at this expression here where we have the exponential of minus alpha times y, which is the label of example I, and h of x, where this is the predicted label for the example I. Remember also that y could be only -1 or +1. So this expression appears, let me go back, in the step 3 of the algorithm, exactly here. So we use this number to change the value of the weights of each of the examples I. So if one example I is correctly classified, this is going to be, this product y times h is going to be +1, and this negative number will remain here, because remember that alpha, we just saw that alpha is always a positive number. So if the example I is correctly classified, we will have here minus alpha, and the exponential of some negative number will give you a number which is less than 1, so it's a fraction. And when you multiply that by d, you will reduce the d in the next time. But if the example is correct, it is misclassified, then here you will have a -1. -1 times minus here is going to be positive, and the exponential of something that is positive here will give you a number that is larger than 1. So 1 something, and that is going to multiply d, and the result of that is that the next time, the weight of that example in the next time will be increased, because you will be multiplying the previous value by a number larger than 1. So that's what this slide here analyzes. So if your current weak classifier HT classifies correctly the example I, then the exponential will be the exponential of minus alpha, and that is going to give you a number smaller than 1. Otherwise, if the example is incorrectly classified by that weak classifier, then this expression will be the exponential of alpha, which is a positive number, and the result of that is that this exponential is going to be a number larger than 1. So the weights of correctly classified points are reduced, and the weights of incorrectly classified points are increased. So incorrectly classified points will receive more attention in the next run. Okay, in the step 3 of the algorithm, you also see a normalization factor, which is called z in time t, or the z factor for weak classifier t, and that is defined as the sum for every example of the products of the current weight for that example and the exponential of minus alpha times y times h. Okay, so that's the definition of the normalization factor, this z factor. Now, we can divide this expression in two parts. In this part in the left, we are computing the sum, but for the examples that are correctly classified. So this stylized A refers to the set of correctly classified points. And we saw that for the correctly classified points, the exponential that we compute is minus alpha. And to the right, we see the same expression, but for those examples, this A bar means the set of examples that were incorrectly classified. And we know that for incorrectly classified examples, we compute the exponential of positive alpha. So we have simply divided this expression in two parts, one part for the correctly classified and one part for the incorrectly classified points. And we can think of this normalization factor as a function, and this is what we are writing here. We're saying, okay, let's consider this factor as a function of the current weak classifier t and its corresponding confidence factor, which is the alpha of t, the alpha in t. And since this expression of this factor z is a way to measure the error of our current classifier t, we want to find a pair of classifier and alpha that minimize this measure of error. And we can do that. So we are interested in some optimal pair star or optimal pairs of weak classifier and alpha that minimize this function. So what we can do is take our function and compute the derivatives of this function and make that equal to 0. Okay, so the derivative of the z function is this one. So the only difference that you see here is that since we have an exponential here, and you compute the derivative of this, you get this minus now as a factor here. And the same here. You have a positive sign here, then when you compute the derivative, you just get here a positive 1. Once we have this, we equal that to 0 and then solve for alpha. So we have this expression. First, what we do here is solving for this factor here. So we move this to the left side. Okay, so we have this equal this, and we move this factor here to the right side, so we have it as a denominator. In the next step, we simplify this, since we have the same thing, the exponential here to the negative number. So when we move this to the numerator, then we have the same but positive, so we have 2 times alpha. And at this point, we can remember that the way we define the error of a specific classifier is simply the sum of the product of the current weight for that example times this function delta, which this function delta, you will get a 1 when you have a misclassified point, and you will have a 0 when you have a correctly classified point. So you are counting all the examples that were misclassified, and you will be summing the corresponding weight for that example. So we can define the error, or this is, in other words, what you're saying is simply summing all the weights of the examples that are incorrectly classified with this set A bar. So what we're going to do next is to replace or substitute this expression in this expression up here. So we are going to substitute this expression here. So what we get is that instead of having here this sum, we will write epsilon, okay? And instead of writing this, we will write 1 minus epsilon. That's because this is the complement to this one. So you get 1 minus epsilon equals epsilon times the exponential of 2 times alpha. Now, we remember that we are solving this for alpha. So first, we move this to the other side. So we can have the exponential of 2 times alpha equals this over epsilon. Then at this point, to get rid of this exponential, we can apply the natural logarithm to both sides of the equation. So this exponential will just disappear, and we will get 2 times alpha here. And this will be the natural logarithm of this expression. Finally, this 2 factor here will go to the side as a 1/2 of the natural logarithm of this expression. So if you remember, this is the formula that you used in step 2 of the algorithm. This is the way you should compute the confidence of a weak classifier as a function of the error of that classifier.